All right, so Greg has shown everyone how to do some basic things with Spack. We're going to go back to a high level and go over some core concepts now that you've sort of seen how the tool works. After that, Greg's going to do configuration and show you all the details of how to make Spack do what you want. It sounded like from this morning that will answer a lot of people's questions. And then Greg will also do a tutorial on making your own packages. So, for core concepts, what's Spack really doing? Most of the existing tools for package installation don't support combinatorial versioning. And this is the basic thing that Spack does that makes it flexible enough to do all the things that we've shown. So if you look at binary package managers like RPM, Yum, APT, YAST, all the system ones, they're really designed to manage a single stack. And so you have whatever's in /user and user lib, user include, all that. That is what you're installing. And the packages are basically sets of libraries, sets of headers, sets of executables that go there, and they're designed not to conflict with each other. They can all be installed in one prefix. Spack is designed to manage lots and lots of different versions. So you could have 16 versions of the same package, or infinitely many versions of the same package if you wanted to. And we wouldn't complain about that. We keep them separate. And everything goes in its own separate prefix. Port systems. So I think people have heard of BSD ports, Portage, Gen2, Mac ports, and Homebrew. They're similar to the binary package managers that are used at the system level in that they're building a single prefix for the most part. They're just installing it from source instead of from binary packages. And there's not a lot of support among those systems for parameterizing builds by compilers and dependency versions. So this is another place where Spack is different. In Spack, the packages are heavily templated. And so you write one recipe, and you can build that same recipe with different compilers, with different versions of the package, with different options, and so on. And it may have different dependencies and different configurations and things like that. We're much more flexible at that level, I would say, than stuff like Gen2 or Homebrew. And then finally, we get asked a lot, well, why do I need Spack if I have virtual machines and containers? I can already build all my stuff in a container. Containers are great. We like containers. They're really useful for snapshotting a configuration, for saving it, for distributing it. But somebody has to build that container. And so, I've heard people say, oh, well, containers solve all my dependency problems. It's fine. And the only reason the container solves your dependency problems is because the system package manager is in the container. It's the package manager doing all the heavy lifting. And Spack is basically a more flexible package manager that you can use to build HPC and other scientific software. And you can use it in a container just like other things. And so it's a fast way to do container builds. There's actually a pretty cool presentation by someone in the high energy physics community, I think from CERN or someplace like that, where it's kind of amusingly named Dr. Spack Love, How I Learned to Love the Package Manager, or Stop Worrying and Love the Package Manager. It's about how one of their developers used Spack to basically make portable container recipes. So they made portable Docker files that could be built easily on different platforms. And he showed how much code that took without Spack and with Spack. And so I think you can think of it that way. It's a cross-platform package manager that you could use inside of a container recipe to build things. It makes your build description much more portable, and it handles a lot of the details for the packages that you want to build. We'll talk a little bit more about that when we get to environments later on in the afternoon. But this is sort of the crux of Spack. And so how do we do that? If you're building lots of different versions of something in Spack, such as this graph here, if I want to build different versions of it, how are all those packages actually installed on disk? And so in Spack, you can think of the graph as these are just the names of the packages, right? And this is showing their dependencies. So MPI leaks depends on MPI. It depends on call path. It depends on dynance, libgorf, libelf. Dynance also depends on libelf. And call path also depends on MPI. If I have a graph like that, you can think of Spack's configuration as basically that graph, but with a lot more details on every node. And so think of it as, this node has the compiler attributes on it and the variants and the different options that you built with, what it actually depends on, and so on. And all the other nodes have that as well. And then take that configuration, put it in a canonical form and hash it, and that's what Spack's install structure looks like. So basically every node in this DAG gets a unique hash, and that determines where it's installed. So under Spack opt, if you want to look in the Spack installation, there's a directory hierarchy that looks kind of like this. I think it's changed a little bit since we made this slide. But each package gets a directory with its version, or its name, its version, and then the hash that represents its full configuration. And really, we could install all of those packages with just their hash as the name for the directory if we wanted to guarantee that they were unique. But we've provided this other stuff so that we can actually read what's installed. We like the directory hierarchy to be semi-navigable at this level. Like Greg said this morning, and we install everything in Spack with our paths in the binaries. So the libraries and executables installed in the MPI leaks directory, they know where the libraries for call path, MPI, dynins, libdwarf, etc. live. And they have our paths embedded in the binaries. So like the library actually has in the ELF format or the Mach-O format an attribute that says, here's where to look for libraries. And that's actually searched before the system LD library path, if we're using our path straight up. You can actually use Spack on systems that use run path as well, and then it's lower priority than LD library path, although you may run into problems there. So if people have questions about that, we can deal with them offline. But the idea here is, and we said this earlier, you knew what you were doing, or at least the package manager did when you built the package, right? That's when you know what all the dependencies are. That's when you're building. That's when you install the thing, and you know what you built with. By the time you get around to running it, you may have forgotten all those details, especially if the thing has 100 dependencies. You really don't want to have to know the library paths for 100 different installation directories to run something. And so that's why we embed the R paths here. And also, the person who runs the binary may not even be the person who installed it. And so relying on things like LD library path basically puts that burden on the person who has to run the binary. So Spack also has this specification language, which we call specs. And these can constrain versions of dependencies as well. And you saw this earlier. So you can say Spack install MPI leaks %Intel at 12.1. Let's say build with the Intel compiler version 12.1. And you can specify a constraint on a dependency using this caret sigil. And so what does that really mean? If you have a graph like this, essentially this depends on constraint means I know that this package depends on libelf somehow, right? And I don't necessarily have to know the structure to express that. I just say, okay, I'm going to constrain the version of libelf because I know when I built with 0813, it broke, and I want to build with 0812. So I can say, install this thing with libelf version 0.8.12, and Spack will go and it will build this whole DAG where libelf is constrained in that way. The user does not have to know that MPI leaks depends on callpath, depends on dynins, depends on libdwarf, which eventually depends on libelf. They just have to know that libelf is in the DAG somehow. And then the other thing that we ensure, that may or may not be obvious from this, is that there's only one version of any particular package in the DAG. So like if you build this and you build dynins with libelf 0813, and then you go and install this, it's going to build a new libelf, a new libdwarf, a new dynins on top of the new version of libelf and libdwarf, and so on, to ensure that everything's binary compatible. So basically, we make sure that the full configuration of any package includes all of its dependencies, and that's to be conservative about ABI compatibility. So on that same note, Spack handles ABI-incompatible libraries like MPI. And so one thing you may have noticed about this graph is that this node here, it says MPI, but MPI is not an implementation. It's an interface. And there are implementations like mpitch and bappitch, OpenMPI, things like that. But MPI itself is actually just a standard, and it's version. And so we call this a virtual dependency in Spack. It's basically, you could think of it as an interface. And you can install the same package but with two different MPI implementations. And this may not be obvious here, but when we say that call path depends on MPI, MPI leaks depends on MPI, what that means is in the recipe you write depends on MPI, right? And so you don't have to write a package for the mpitch version of your code and a package for the OpenMPI version of your code and a package for the bappitch version of your code. You just write one package. You say it depends on MPI, and you can swap in different MPIs at install time. Yep.
I don't think that would work because mpitch derivatives and OpenMPI derivatives I don't think are ABI compatible.
That's right. They're API compatible. So think of this as a source interface.
Okay, source interface.
And we will rebuild on top of things.
Okay.
Right. So like that, and it's only API compatibility that's required for a virtual dependency in Spack.
Okay. So once you are moving to like binary, instead of building from source.
Yep.
Is there any way to mention ABI compatibility as well? So for instance, like a lot of mpitch derivatives are ABI compatible.
So at the moment, we don't have a model for that. That's something I'd like to model so that we could make the binary installation model a little more flexible so that we could swap in different MPIs for things, for example. But right now, we're pretty conservative about this. And so, and when you actually install the package, the DAG says, the DAG no longer has the virtual dependency in the metadata. It says this is OpenMPI, right? And so the thing knows what it actually was built with and what it depends on at runtime when it's installed. I think that's a really interesting topic, so but we should talk about that offline because we have nothing implemented on that. Okay, so if you want to install the same package built with two different MPI implementations, all you do is you use the same syntax you did before. You can say Spack install MPI leaks depends on mVapage at 1.9. And that says install this with mVapage at version 1.9. Install MPI leaks depends on OpenMPI at 1.4 or higher. It's something else you could say. That just says I need OpenMPI at least this version. And then finally, you could be less flexible about this. This is really for the sake of example. You could say Spack install MPI leaks depends on MPI at version 2, which just says find me some MPI provider that supports MPI 2. This kind of constraint is really something that someone would probably write in the package. So like you can actually say this package depends on MPI version 2 or higher. And Spack knows the version of the interface, and so it will match your MPI requirement with a provider that provides that version of MPI or higher. And so these kinds of things like OpenMPI 1.4 or higher or MPI at version 2 are the sorts of things that you would write in a package and not necessarily on the command line.
So can I write a package so that if, like, for instance, if I have an MPI with MPI3 compatible, would this check kind of catch that, or would it actually check for the number 2?
This specific one would say, this would actually match something that provides 2 or higher.
2 or higher.
Yeah, or 1 or higher, right? Like so this would be fine. The other thing that we'll get to in the packaging section, or if you just look at any of the MPI packages in Spack, if you just do Spack edit OpenMPI, the package can provide different versions of the MPI interface when it's at different versions. So you can say OpenMPI provides this version of MPI when it's at version 2 or higher, right, and so on. So like the mpitch package actually says, or I think the mVapage package, it started providing 2 in 1.9?
Yes.
Yeah, so the mVapage package says I provide MPI at version 2 or higher when I'm up to version 1.9, and so on. So, yep.
Is there a way to specify rules if neither of those packages are installed, which one to pick when the user has specified this? Can you say, for example, that prefer this over that?
Greg will cover that in the configuration section.
Okay, good.
We keep saying that. We need to cover. We need to spend a lot of time on configuration. Okay. So, what are you doing when you say Spack install something? So when you issue these commands, what's really happening behind the scenes? We have this algorithm called concretization that basically fills in missing configuration details and where the user is not explicit. And so if I say install MPI leaks depends on call path at 1.0 plus debug, depends on libelf at 0.8.11. What really happens there is Spack takes that spec and it makes an abstract DAG. And so we call this an abstract spec. Or this is an abstract spec. This is sort of the abstract graph that we built from it. MPI leaks depends on this package. You can see that the constraints from the command line are on that node. It's only depending on MPI at this point, and then the constraint on libelf is there. We take that thing and we do something called concretization to it, where we basically look at all the constraints on the packages, we look at the constraints that the user provided, and we come up with versions and compilers and architecture specifications and variant values for all of the packages on the graph. And this is what you get once concretization is finished. And once that's done, we actually store the concrete spec as YAML in the installation directory. So we maintain that full installation data, both in a database and in the install directory for the package. I think it turns out that this problem is actually NP hard, the version selection problem. So if you're given a set of constraints and you have to find a set of package configurations that satisfies them, that's an NP hard problem. We're currently using heuristics for this, but we're working on a new version of the concretizer that will do a lot more backtracking and smarter solves for this part of the pipeline. Other systems do this, but I think that for the most part, they do it with just the package and the versions. And they look at version incompatibilities, and we're actually doing this on the compiler configuration, the variants, the build options, the optional dependencies, and things like that. So it's a lot more conditions that you can put on a package and a lot more possible configurations that you can build with a Spack package. Yeah?
Will we be talking about the innards of the Concretization model?
We will not. But if you want to, we could totally talk about that like during the free time tomorrow for building packages. Yeah. If you want to see how a spec was actually concretized, then you can say Spack Spec. So you can say Spack Spec, MPI leaks, and it'll print out what that thing looks like concretized. So this is a useful way to see what Spack would do if you wanted to install something. And it'll spit out basically everything that it fills in. There are options on this to show more or less options in the output. I'm not going to cover this in too much detail, but we do support something called extensions for Python. If you know much about Python, you know that the Python extensions or modules like to be installed in the interpreter prefix. And so this is sort of counter to Spack's model. What we do to address this is we model everything so that it's actually installed in separate prefixes. So for Python, for R, for Perl, all the extension modules for those things are installed in their own prefix. You can choose to have a set of those activated in the interpreter prefix, and we will symlink in the modules to the interpreter prefix. And there are ways to control how that happens. The disadvantage of this is that you're sort of pre-installing some things into the interpreter prefix. You're actually modifying it, and so you may have some other modules that are now incompatible with that interpreter. And so the other way that we support this is through environments, and we'll talk about that later on today. You can have a Spack environment where you activate different Python packages, and this is sort of a replacement for this older activation thing. But you can do this in Spack. And you can activate and deactivate packages just as you wish. So if you want to have one version of NumPy installed today and then you upgrade it tomorrow, you can take it out and install a new version of NumPy in your Python interpreter. I don't want to get into the details of that. We support building against externally installed software. This is something Greg's going to talk about in the configuration section. But essentially, we have a file called packages.yaml where you can basically say, I don't want MPI to be buildable, and I don't want OpenMPI to be buildable, and here are some installations of OpenMPI that already exist on my system. And so what you're saying here is to Spack is, I have an OpenMPI that matches this spec right here. It's OpenMPI version 2.0.0 built with GCC. It has this architecture, and it's installed in this path. And that's pretty much all you have to tell Spack to have it support an external package. So the thing that you lose there is you lose all the provenance that goes along with the package. So if you have MPI links built here, and it has OpenMPI 2.0, if Spack had built it, we would know all about all the things that OpenMPI depends on. But because you've just told it the path to some external OpenMPI, we don't know anything about that. And so we basically cut off that metadata in the installation. This will have a different hash than what you would have gotten.
Would you just request the remote users to mute their mic?
Oh, okay. Hey, remote folks, can you please mute your mic? Yeah, can you mute them from your? Do you have the?
I can't
console?
Who can mute them?
Who's the host? Maybe Shandon. I actually don't think I have privileges to mute.
Do that.
How many people do we have online?
17 plus.
Nice.
Africa.
23 people.
They've got a challenge in terms of network.
Shandon around. I can get him to.
Okay, great.
We're good? Okay, awesome. All right. So the final thing that I wanted to talk about in this section is, well, there's two more. So for package repositories, Spack has a lot of different places where you can store package recipes. When you clone the repo, in var Spack repos built in, this is where the 3,200 packages that come with Spack live. And you can also have repos that are just local to your site. So you can say Spack repo create, it'll make a special directory, and you can create your own package recipes there. You can have sort of a hierarchy of repositories. You can have as many as you want, where in your own repository, you might put your own proprietary packages. You may put modified versions of Spack's built-in packages to handle weird build cases for your site, or you may extend them. And then beyond that, you may just have standard packages that go in the built-in repo. You can actually leverage all of these standard packages from these two places. And so we use this at the labs because we have a lot of export-controlled codes. And so our export-controlled stuff lives in a Git repo internal to Livermore, and we develop our packages there. But those packages actually depend on a lot of the open source things that are in the main Spack distribution. So for things like MPI, we don't necessarily have to maintain that internally, or for other types of open source dependencies, but we can still maintain our internal packages and have them leverage the upstream repository pretty. Any questions on this? Okay. We may get into this in the configuration section, but I think it's fairly straightforward to deal with the package recipes. Yeah.
So is this the way that I would potentially create a like mirror or a repo for others to use?
This is different from a mirror. So a mirror is where you store source code or binary packages, right? So the actual artifacts that you need to build something.
Okay.
This is where you store build recipes, okay?
Okay.
So if you think about the interface that Greg showed, when you type stack list to list what's available, that shows you the names of packages. Those are templates, right?
Okay.
This is where those recipes go,
Okay.
right? And then if you type stack find, right, or if you type stack install, it's going to fetch a tarball for those things or patches or other resources from the internet.
Okay.
Those go in a mirror, right? And then likewise, if you install something and create a binary package out of it, that goes in a mirror too. But this is just the recipes. Okay. And then for fetching source code for Spack, there are these things called mirrors. If you say Spack install MPI leaks, what's actually happening there? The first thing it does is it loads a package recipe from the repository. So this is the recipe file that we just talked about. It concretizes it. It recursively installs all the dependencies. And for each of those, it goes and fetches the package source. And so it looks in a few different places. So it looks in a user cache. And so this is actually within the, I guess this is within the Spack repository here. It can look in a mirror out on the internet, so like a configured mirror. And then it can go, actually the mirrors can live either on the internet or they can live in your local file system. And then it will go out to the internet and actually fetch Spack packages from where they live. So if you look at the actual Spack recipes, usually the URLs for tarballs are basically at the originator's site. So if it's mbitch or mbapitch, like it would, if it's mbapitch, it would come from Hari, wherever he posts the latest tarball for mbapitch. If it's OpenMPI, it would come from the OpenMPI website, and so on. Mirrors are basically caches of that you can configure and put somewhere so that if the site goes down, you can still download those tarballs. And then actually whenever you fetch something, there's a mirror that's built in the Spack directory on your machine where we just cache all the tarballs that you've ever downloaded. And there's a Spack clean command you can use to get rid of that if you want to, if you run out of space, for example. So that's sort of the ins and outs of how source code is fetched with Spack. And you know, I think that's fairly straightforward. There are sections in the docs on how to configure this stuff and how to add mirrors to Spack. We already talked about adding custom compiler flags in the hands-on session, so I'm not going to spend too much time on this. I guess one interesting thing I will mention, and you know, you saw this in Greg's tutorial, is that the compiler flags are actually included in the metadata for the package. So if you want to build the same package with different compiler flags just to do experiments, you can actually use Spack for that. All right, so now I'm going to turn it over to Greg for configuration. Where is Greg? I think for this, we're going to go back to the script and
Do you turn SPEC on by default?
most packages just do. Yeah, that's usually handled by the builder.
Okay.
zlib has it as an option in the Spack package,
So again,
for example.
We're still working from the tutorial materials. I think everyone's found them, but I've tried to write the URL vertically here. It's bit.ly/stack-tutorial. So if you want to find the scripts that we're going from, they're here. And this is also written vertically over there.
So configuring Spack, I got a lot of questions earlier. The answer to which was, I'll talk about that later when we talk about configuring Spack. And there's a lot of different ways that you can configure Spack. I'm going to get that out of the way. Do you have a power cord on you, Todd? Yeah, I'm going to go steal this.
Okay.
Sorry.
It's on this side. Very good.
Sorry for that. That'll keep the screen on. So the first thing to talk about with configuration is where we can configure. And someone asked about, do we have a system or a site or system config scope. There are, in this diagram, we talk about 6 different configuration scopes in Spack. In the environment tutorial, we'll talk about even more ways you can configure Spack. But that's better. So Spack ships with a default set of configurations that set things like, we prefer GCC to Clang, we prefer OpenMPI to MPitch, and a lot of these choices are somewhat arbitrary. They're just set so that it does something out of the box. If you clone Spack and say Spack install HDF5, you get something. But you might want to change those. You might want to change them at a system level, as an HPC facility. Say, hey, we've published binary mirrors in this place. You can do that in etc Spack. As a team, if you're sharing a Spack installation, you can put configuration in the Spack root etc Spack. User configuration, and this is generally the default scope, gets put in the user's home directory in the .spack directory. And then you can also, from the command line, say spack-c or --config scope, and get, add whatever configuration scope you want into that. And then command line is only sort of a configuration scope. There are options on the command line that are handled internally as configuration. In each of these settings, or in each of these scopes, there's also a platform-specific scope. So if you are on a Cray, it will look in etc Spack/Cray. If you're on a BGQ system, etc Spack BGQ. On Linux, Darwin for the Mac platform, etc. Within each scope, then we use YAML files for our configuration. And there's only one thing we've changed from default YAML in Spack. We've added this double : key that you can see here. And what that allows you to do is to override the previously read config scopes. So we read the scopes in increasing order, preference order, and we merge the configurations into a giant dictionary in Python. And this says, hey, throw out everything you've already seen for this key. Don't merge it. Just take the new stuff. All right, so let's dive into actually configuring something. So I'm going to set my editor to be Emacs. By default, it will use VI. Leave it as whichever you prefer. And then Spack config edit compilers. So for compilers, by default, you will edit your user scope, the platform-specific user scope, because compilers are generally platform-specific. And here we can see the file. And this is all the same. These are the same 4 compilers that we saw when we ran Spack compiler list earlier. So if you look at the Clang compilers here, these are the first 2, you'll notice there is no Fortran compiler for them. Generally the case with Clang. Maybe Flame will take off eventually, but generally there's no Fortran compiler for Clang. So I mentioned earlier we could create a Franken compiler that has Clang for C and C++ and uses gfortran. And that's exactly what this is. I'm going to take that and did not want to paste nicely.